All right, I'm gonna, oh, there we go. Can you all see that? EN15978? Yep, I think so, good. Just about visible, just about legible. Okay, try and sear that number in your minds and back of your retinas. This is 2017 European number, European norm, which effectively covers the embodied carbon of a building across its lifespan. So sections A are the materials, their transportation, construction on site. Section B is the operational embodied carbon across the building's lifespan. And then C, what do you do with those materials at the end of life? In other words, when you're demolishing, where do they go? Now, section A alone is around about 60%, including, so if you, section C is about 2%, section A is about 50-odd%. So together they're around about 60% across a building's lifespan, making section B, the operational carbon, the minor, 40%. Now, that is a good way of measuring the embodied carbon across a building's lifespan. What it doesn't do, though, is tell you what the material, the embodied carbon of those materials are. The next slide. Is the sound okay? You're not getting feedback or anything?
It's all good.
Okay, splendid. Now, we came across that a few years back. It's all very useful, knowing that the embodied carbon of a building is mostly its materials. So when I was studying many years ago in Edinburgh, our tutors there told us that the materials were no more than 15%. The embodied carbon of a building was mostly its operations. So what's happened since then in that time? It's basically equipment has got far more efficient than it was back then. And of course, now we insulate properly. We have building codes that make sure we insulate well and we double glaze everything, so on and so forth. So inevitably, the materials haven't changed a great deal, but we burn less energy on heating, cooling, hot water, and so on. So the materials will always be there, and they'll slowly grow in their dominance of embodied carbon. However, most of us are still using BREEAM, LEED, Passive House, and so on and so forth, which really conceptually come from a period when we're trying to burn less energy. They're born in the oil crisis, post-oil crisis. How do we burn less energy for economic purposes? Obviously make buildings more efficient. And then are now conflated, of course, with sustainability. Roughly the same time, 2017, the University of Bath and the British Services Research Institute, BSRI, produced what's called the Inventory of Carbon and Energy. So this listed kilograms of carbon it takes to make a certain material, the kilogram of carbon per kilogram of material, which isn't useful, isn't that useful to most architects. So we converted that with Webb Yates, sustainability engineers. Obviously, they do superstructure and structural engineers and civil engineers, and Bureau Happold's sustainability side, as well as 8 Versa, their sustainability side. Converted that into kilograms of CO2 per cubic meter of material. Then we changed it from an alphabetical order, which is what the University of Bath BSRI inventory does, to highest performing, worst performing, I should say, and best performing. So right at the top, polyester powder coated aluminium, 36 tons of CO2 per cubic meter. And right at the bottom, minus a ton for sustainably sourced hardwood, so just cut into large lengths, beams, and so on. We then color coded that, so you look at them as if they're a supermarket traffic light system. So imagine going to your supermarket and fleetingly saw, as you turn that laptop around, Vanessa, that some of you obviously go in there and fill the supermarket trolley with all the red zones. It's high, it's all alcohol, high sugar, what is it, salamis, bacon, having a great time. We're going to go to your party and have a great time, but obviously you're not going to live long, and we won't live long if we carry on going to your parties. And right at the bottom, if anybody's going to Vanessa's dinner parties, kale, boiled kale. Anyway, so you get the picture. There's a menu there of materials, some of them very good, some of them not so good. And it's not about eliminating the not so good. It's just about saying, well, Vanessa actually deep fries some lardons from the red zone and sprinkles them across the boiled kale, and voila, we have a delicious meal. It's exactly the same thing with buildings. Now, yeah, sorry, have a look more closely at that list, and you'll see that from the bottom going up, to our surprise, the BSRI still has things like MDF as minus, as in there's still carbon sequestrating. Now you have to remember, not every country counts the sequestration of timber because we don't know what to do with it, what happens to it at the end of its lifespan. So typically in the UK, it's not counted at all. While in France and Australia, as soon as you use a bit of timber, you're counting the sequestered carbon. There's a thought experiment though, before I move on. If we make our building 100% out of timber, it's a carbon negative building. It's a carbon sequestered building. So the thought experiment really says we should all be using vast amounts of timber, cut down as many trees as we can, and have a building boom because we're going to sequester CO2 out of the atmosphere. As long as it's a sustainable forest and it's not going to disappear, we should all go building mad in 100% timber. Now, interestingly, Michael Rummage at Cambridge has done a survey, his students have done a survey of EU, so forests across Europe. And some time ago, there was investment in commercial forestry because they thought demand was coming, and it has come. But at the moment, it's growing faster than it's being cut down, and it's already sequestering about a quarter of EU's emissions. Tom Crowther in ETH Zurich has done a similar study of land that was cleared. So, a couple of years ago, I was up right in the furthest north part of Scotland looking at CLT building, marveling at the romantic landscape when, a local tapped me on the shoulder and said, "You do realize this is just a biodiverse desert. This used to be biodiverse woodland, mixed woodland, before it was all cleared." So Tom Crowther at ETH Zurich has done a survey of all the cleared land that is no longer being used for agriculture or even development. And they started off in Europe, and they eventually extrapolated it across the world. And some of you will know in 2019, they wrote this paper, which effectively got picked up and sort of slightly caricatured. Plant 1 billion trees and we'll sort out atmospheric carbon. What the research showed is that if you plant in cleared woodland that's no longer being used for agriculture or development, within 100 years we'll be at pre-industrial levels of CO2. These are optimistic ideas, obviously. So let's just have a look at the current state. If we're looking at that list, as you go up, you'll see stone suddenly appears. From timber, there's stone. The stone obviously has zero carbon. It's sitting there, made hundreds of millions of years ago, sitting below our feet. It inherits some carbon if you're using diesel equipment to cut it out. If you're using diesel equipment, it'll still be a sort of cubic meter block, 33 kilos of CO2 per cubic meter. Once you cut it up into bricks and cement block sizes, obviously it goes a little higher. And depending on the machinery you're using, and what else you're doing in the stonemasons, it could be as little as 50 kilos per cubic meter of stone. Now, compare that to steel at one end, cement, reinforced concrete, fired clay bricks. You'll see when people say, but surely we're going to run out of stone, but surely the planet will be covered in quarries. People forget that steel comes from a number of different quarries. I can never remember the exact amount. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. That's 11 just for mild steel before you then add different alloys to make it stainless and so on. So those are all different quarries, all of which then have to be fired up at 1600 degrees C to create mild steel before it's then formed into beams and columns and so on, and sections. Cement, it's another 8 quarries or so, one of which is limestone. So you take the limestone block, smash it, pulverize it, mix it with a bunch of other things you've extracted from quarries, burn it at 1450 degrees C, and bang, you've got some cement. You've got a bag of cement. To make concrete, you have to take that cement, sharp sand, aggregate, water, admixture, release agents. And at that point, the cement with all those other things has got about 40% of the original limestone strength. So you have to put steel in there to reinforce it, to bring that strength back up. So you can see there from 10,000 kilos, so 10 tons per cubic meter of CO2 for steel. Reinforced concrete can be anything from 1,000, depending on which part of the building it's on and how much reinforcement you're using, to 2,000 kilos of CO2 per cubic meter. Fired clay, the same. You're using 6 to 8 different quarries to make your clay mixture before you then warm it at 100 degrees C to get some of the water out, and then fire it at 1200 degrees C. And then there's natural stone and obviously timbers. So the stone is about 99.8% less than the mild steel, 98% less than the fired clay bricks. And obviously the timber is carbon sequestrating. I'm just going to swap to a building to show you what you can do. You bear with me a second. There we go. Oops, did I do that? No. Bear with me a second. I think it's that one. No, it's that one, yeah. Okay. So Barrett's Grove initially came about from our original sort of way of looking at it, came about from a client simply telling us, I think I've paid too much for the site. How do I get the construction cost down? And we said, well, look, if you make the entire thing, walls, floors, roof, internal walls as well, internal partitions, etc., out of CLT, and the other products that come out of it, so smaller, basically like larger bits of plywood for internal partitions and cabinetry, then put an overcoat of mass insulation and an external rain screen that sits on the ground, is not suspended from the superstructure. Now, most of you will know, if you're all architects, so you sit in the office and you're happily drawing away a brick facade, and the engineer will tell you, well, it needs to go on a brick hanger per floor. So now, you know, the answer really is you don't hang the bricks from the floor. You allow those bricks to hit the ground, because the bricks, whether they're fired clay or stone performs better, can sit on the ground and rise up half a brick thick, 6 floors without any engineering. You know, they can take their own weight. They just need to be brick tied back to the structure. So you can see there, the structure is essentially the internal finish. It's CLT. Now, at that time, the agent to this client said, "Oh my God, who the hell's going to live in a CLT, Swedish sauna? You'll never have people rent these or even or buy them." But we worked out the cost saving. You can see there the detail that floors, walls, roof, super installation, a cavity, and then a rain screen of bricks that sit on the ground, basically means you have no hangers. Bricks are just sitting on the ground, which means the superstructure is about 30% lighter than it would be if it was trying to carry the bricks. And most of us forget when we're putting brick hangers in, the superstructure has to get bigger because it's no longer just carrying us, the interior, but it's having to carry the skin at the same time, a heavy masonry skin. So you saved on your superstructure, but because the internal finish is also the superstructure in this condition, you've saved on your plasterboard. So your aluminium lining, the plasterboard, the skim coats, the painting, the architraves, skirting boards, and so on. So you saved on material, you saved on labor, and you've saved on time it takes to do all that. That together saved the client about 25%. And this client's ignored the agent and said, "I'm going to take a risk. I will, I'll do it. And if nobody buys it or moves in, I'll send the paint team around." So that was the outcome there. And in the end, it's not a huge building. It's in central London. It's a reasonably large population. It was all bought by Swedish people. So it paid more than. I'm kidding. I think there might be one Sweden though, but who paid more than the going rate. But you can see there, we tried this exercise on consequence of using quite a lot of timber. You can see as a consequence there, so there's a lot of material, and the resolution's not so hot. There's a lot of timber material, CLT, in there, and you end up with a carbon negative building. Now, the reason you can count carbon sequestrating materials in this country, in the UK, is if you put a planning condition, Section 106 agreement, a planning condition in, which we already have. So you don't need to change legislation. You just put a planning condition, the same as you would have, that says you can only use this material on the facade. Your windows must be made of this. The brick has to be red or whatever. The stone has to be this, that, and the other. Normal planning conditions. If you put a planning condition in saying, when the building is demolished, the materials must be reused, including the timber, that is all you need to do. Because then you've done what's called material passporting. You've given the material an identity and a legal condition that should the building be demolished next year or in 200 years' time, whoever has the building at that point is required to ensure the timbers are reused and therefore the carbon's locked in. So at that point, you can count your sequestrating carbon. You've done something good. You've got out of bed, you've designed something, it's been built, you've taken more CO2 out of the atmosphere than putting it in by doing nothing, which is a different paradigm from, let's say, 10, 12 years ago when it was degrowth was the solution, which, is sort of embarrassing because I don't know how many talks you go to, there's always somebody who says, why don't you architects just build less? That'll be the answer to our problems, forgetting that actually the rest of the world doesn't go home to centrally heated apartments or houses where you can flush the toilet, get fresh water from the tap, have your rubbish collected, and they will, won't they? They're all coming. They're all coming to the same living standards as we are, and by 2050, we're projected to more than double what we've already built across the planet. So if we don't show how it can be done better, why would they? Okay, I think I'm going to take you through one more example, building example. Okay, whoops. There we go. So this is a stone timber hybrid, 10 stories tall. It still hasn't topped out. I think we're topping out in a month or so, where the stone is the exoskeleton. And actually, originally we thought the core was going to have to be a lot of mild steel. So it doesn't have to be. We're now making the core, so that's the riser, the services riser, as well as the lift and stair core out of stone. So these are basalt blocks cut to breeze block size. That's all it is. There's no reinforcement in there at all. Rising 10 stories to take the lift and the riser, and then strapping the lift around it. And you can see there the rest of it's then CLT. So that's the plan with this one, which hopefully will be done relatively soon. Right. So I'm just going to try and work out how to share an Excel document, because I want to show you. We've gone from not just the embodied carbon of buildings, of materials, but also of right. How do I share an Excel document? That's not so easy, is it? Oh, window. There we go. I think I found it. Okay. Yeah. So can you see that?
Yes.
Yeah. All right. Right. So there is a scheme we submitted not long ago, where by now we've learned that if you hybrid basically timber and stone, you'll end up with a carbon negative building. So you can see there, we've gone from bits of steel and brass at the top, glass and so on and so forth, until you get down towards the bottom, there's stone, still positive because there's, I can't remember how many, 353 cubic meters of stone, which gives us 61,000 kilograms of stone. But then the rest of it is quite a lot of timber in the floor plates and other pieces of structure, that the outcome is still negative, in all that mixture. But in addition to that, this is one of those colleges where they've got lots and lots of grade 1 listed buildings. You can't even put double glazing in, you can't put insulation on the inside, you can't put it on the outside. So how are they going to insulate these? And we said, look, you've got plenty of ground, we've got plenty of facade for PVs, but you've got so much ground, courtyards that nobody walks on, of course, grassy courtyards. Why don't we lift them up over the summer and put lots of ground source in them, put turf them back over, and see how much energy we get from that, plus the PVs. And of course, it turns out we've got far more than this library and new student hub needs. And we can give it to the grade 1 listed buildings that are adjoining us. So you can see there in terms of, there's the lifespan of the building, expected to be 200 years. But there in column Q, the kilowatt hours that is counted as minus because we're now producing it on site. It's an on-site renewable, and it's minus because we're not taking it off the grid. So it's the equivalent of not taking off the grid, as it were, by being on site. So you count that as minus, and you end up, of course, with going off the grid, a double sort of negative, if you like. And you can see there, across 200 years, the materials, despite being carbon negative, are only 1% of the embodied carbon across its lifespan. The rest of it's the operational carbon. But nevertheless, it's also a minus. So you end up with a minus kilogram of CO2 per square meter. At the moment, the RMBA is hoping everybody's about 500 kilograms of CO2 per square meter. So these things are possible today. And if there's a takeaway for you all, hopefully I can share this with somebody at your end. And it's fairly, this thing comes with instructions. There's an instruction guide there. Tells you who to phone at the bottom if you've got any problems. Yeah, I'll leave you with that. Okay.